Hey everyone, welcome back to physics. This will be lecture 29 of the course. And in this section, we're going to continue with our exploration of potential energy by discussing another type of potential energy, in this case, elastic potential energy. And so a lot of the derivations and the notions that we arrive at in this section will mirror what we talked about in the previous section, gravitational potential energy. So it'll be a slightly shorter section, but it'll have a lot of the same concepts. It'll be shorter because it has a lot of the same concepts that were taken from the previous. So let's go ahead and get started. And we'll call this section 6.2 elastic potential energy. So the first thing to discuss is, what do we mean by elastic? And I think a lot of people hearing that term will have an immediate sense for what we mean. But let's take some examples. I think one of the most obvious examples is the example of an elastic band or a rubber band. This is an elastic body. Right, so we all know that if you have a rubber band, maybe it looks like this, it'll have a sort of resting state, right? A resting state where it's not stretched. But I can grab the rubber band and I can stretch it, right? And stretch it out very, very far, depending on the rubber band. How far you can stretch it is going to depend. But when I do that, when I stretch it, when I stretch the rubber band or deform the rubber band by pulling it, what I do is I am injecting potential energy into the rubber band, right? Because in its stretched state, kind of like a spring, if I pull a spring apart, it wants to return to its resting state. And so in stretching a rubber band, I am introducing a kind of energy into it. Another example would be an example of like a rubber ball, right? So take like a tennis ball or a springy rubber ball, right? In its normal state, it's spherical, right? It's going to look like a sphere. But if I were to throw the ball very hard against a solid object like a wall or something, then what you would see is that the wall will deform the ball, right? And the ball will sort of squish, its body will be compressed against the wall and it'll deform, right? So the ball gets deformed by the wall. And in doing that, we know that the ball will not stick to the wall. It won't fall directly down when it hits the wall. Instead, it'll bounce back. Right, and so the energy, the kinetic energy of the ball is transferred into a kind of potential energy through this deformation process. Now, in both of these cases, the rubber band and the ball, while these objects are in their deformed state, i.e. stretched or squished against a wall, they have a tendency to revert back to their normal state. And that tendency basically takes the form of a potential energy. And now these are just other examples of kind of the quintessential example, which is the spring, right? So the spring example is the one we'll run with in this section. But, all springs are going to have a kind of a normal state, where they're kind of resting state. So normal state or resting state, where they're not stretched and they're not compressed. Right? Now we know that if we stretch the spring, then it's going to have a tendency to want to shrink back down to this normal state, and that tendency is a kind of potential energy. Similarly, if I compress the spring very tightly, it's going to want to expand. It's going to want to stretch out until it reaches this normal state. Okay, and so the spring is kind of the ideal example of this elastic potential energy. Now, a lot of the formulaic approach we take to springs can be applied to other things like rubber bands and balls. And so we'll operate from the standpoint of describing potential energy in a spring, but just know that a lot of that translates over to balls and rubber bands and things, okay, in the way that you would model those types of energies. So if you recall from prior sections, we did discuss springs. We discussed Hooke's law previously. And Hooke's law, named for Robert Hooke, Hooke's law says essentially that to keep an ideal spring meaning massless, an ideal spring stretched by a certain amount, we have to apply a proportional force. So to keep an ideal spring stretched by x, like some distance, we must exert a proportional force, right? So what this all kind of boils down to is that the spring force is equal to K times X, where K is based on the particular spring in question. So where K is the spring constant, right? So all springs are going to have a different rigidity, right? And so a large K indicates a very rigid spring, and a very small K indicates a very non-rigid spring. And so depending on this K, the amount of force that's required to stretch it varies. Okay. And so let's kind of examine the block on a spring model. And this is the model that we'll kind of run with in describing this elastic potential energy. And so the idea here is, let's draw a couple nice pictures to start with. So let's say I've got a kind of a block here that's on a spring, and it's got some mass, and the spring is attached to a wall, right? And this thing is gliding on a frictionless track. Okay, so I got a spring with a mass m connected to one end of a spring and resting on a frictionless track. Okay, so frictionless track, very important, right? This is kind of an idealized scenario. It's an ideal spring, so the spring has no mass. Okay. Now at rest, we know, right? So if it's just sitting here and the spring is at its resting length, right? It's in its normal state. So at rest, this block is going to have no velocity, right? So we'll call this resting state x equals 0. In its resting state, the block has no velocity, right? And therefore no kinetic energy, right? Now it also has no potential energy, right? This thing's just sitting there. There's no energy in the system whatsoever. Okay, so what happens though when I stretch the spring? Right, let's say instead I stretch this thing out and I stretch it over to here, we'll say. Okay, so somewhat beyond its resting state. Okay, now if I pull the block out to this position, I'm going to call this x1. If I pull the block out to x1, we have stretched the spring beyond its resting state, right? So spring is stretched beyond its resting state. Okay, so we've exerted a force over a displacement, and we've done work to the spring. we have done work to the spring, right? We've done work to the spring, right? We've exerted a force on the spring over displacement, namely this distance here. Okay. Okay. Now, in doing this, the block and the spring are now going to have a potential energy, right? And the meaning that, I mean, just intuitively, you would know that if I let go of the block and it's in this stretched state, it's going to go flying off to the left, right? There's some kind of, I've loaded the spring and the block up with potential energy. Okay. Okay. So this act of doing work to the spring, and I'll just say and block, right? So you're doing kind of work to both of them. This act of having done work to the spring and the block imbues them with some potential energy. This imbues the system with potential energy. Okay. Now, it's important to keep track of the direction of the spring force, right? So think about what happens to the spring force when I stretch or compress it, right? So let's talk about stretching it first. Okay, so if I stretch the spring, right, so that means the displacement of the force is, the displacement is in this direction, right? And so when that happens, the spring force itself is going to be towards its normal state, right? It's going to be this direction. Okay, now what happens when I compress the spring? Right, in that case, so this is compressed. In the case of compressing a spring, right, the displacement is this direction, right? And so the spring will want to stretch back out. It'll want to go back to its normal state. And so the force in that case is going to be the other way. Okay. So the spring force, the force exerted by the spring, is always opposite the displacement of the end of the spring, relative to its resting position. If we compress it, it wants to go, it wants to be uncompressed. If we stretch it, it wants to be unstretched. It's always going to go in the opposite direction of whichever direction the displacement is. Okay, and so let's kind of break down the work aspect on this idealized system that we have up here. Let's break down what's going on as we stretch or compress this thing in terms of work. Okay, so let's say I have my spring system is doing this. I've got so what I want to do, what we want to start with is the example of stretching the spring from x1 to x2 beyond its normal state, right? So we'll say maybe we'll say x1 is its normal state, and I'm going to stretch it out to x2. Okay, so the mass is going to move from here over to here, right? So I'm causing a displacement from x1 to x2. I'm stretching the spring, and so I know that the spring force is going to be opposite that direction. Okay. Now, in moving the weight from here to here and stretching the spring this direction, my hand is going to do going to be exerting a force also. My hand force is going to go like this, right? The force of my hand, I'll write it down here, force of hand. All right, so we got to keep track of all these forces because we want to quantify the work. We want to figure out what's doing positive work and negative work, and keep track of what's what here. So in moving the block from x1 to x2, my hand has to exert a force in this direction, and as I do that, the spring force pushes against my hand in the opposite direction. So the spring force opposes the stretching force. Okay, So the displacement is to the right, which stretches the spring and causes the spring force to be to the left. And so what's going on here? So the spring is doing negative work on the block, right? The spring force is doing negative work on the block. The spring is doing negative work on the block because, right, why is that? Because the spring force is in that direction and the displacement of the block is in that direction, right? So whenever these two are opposite, then the work is negative. So we got negative work being done on the block. But what about the work that our hand is doing on the spring? The hand force is doing positive work on the spring, right? And that's because the force being done by the hand is that direction, and it's also the same direction as the force, or as the displacement. Okay, right? So the hand force is aligned with the displacement, so the work is positive, and that's the work that's being done on the spring. Okay. Right, and so this is the idea of kind of stretching the string further, right? This is what's happening. In stretching the string further, we are doing positive work on the spring, right? That's kind of the takeaway, right? And what about another scenario, kind of similar but, well, different? Let's say instead we're going from this extremely stretched state to a less stretched out state, right? And so let's say that x equals 0 is off to the side here somewhere. And the spring starts out very stretched out, way over here at x2. Sorry, it starts here at x1, we'll say, and it becomes less stretched out, x2, right? So like my hand holds it and slowly allows it to, I slowly move the block over, allowing the spring to compress a little bit. But it's still stretched out. It's still beyond its resting state, right? So in this case, the displacement is in this direction. Right, we're moving the end of the spring, i.e. the block, from x1 to x2, right? So it's in this direction. Now the force of the spring in this case, because we're beyond the stretch state, is still in this direction. Okay, that's the force of the spring. Right, the spring still wants to go further. It's not content to merely move from x1 to x2. It wants to go all the way to x0. That's its normal state. So it's in this direction. Even though my hand is holding the block and moving it this way, my force, I still have a force that I'm exerting, a net force in the opposite direction, right? Because I have to offset the spring force. And so the hand force in this case is in this direction. Okay. All right. So this situation is kind of similar to the previous one, but a lot of the stuff is sort of reversed, right? So we now compress the spring instead, right? We allow the spring to get closer to its resting state. So assuming the spring is still stretched beyond its resting point, then the displacement and the spring force are both to the left. Okay, and that means the spring is doing positive work on the block, right? In moving, allowing the block to move from here to here, it's doing positive work on the block. The hand force is still to the right, and is now opposite the displacement. So the work our hand is doing to the spring is now negative, right? And so here we saw that as the hand moved this direction with the displacement, we were doing positive work, which if you think about it, just means we're injecting more energy, more potential energy into the spring. As we stretch it further and further, the spring potential energy gets larger and larger, stronger and stronger, right? The spring is, the farther you stretch the spring, the more it resists you, right? And similarly down here, but kind of the flip side, is that we start with the string very stretched, and then we allow it to compress somewhat. We take away some of the potential energy, right? So in this case, the hand is doing negative work to the spring. So in this case, the hand force, is doing negative work on the spring. Okay, so up above we saw here the hand forces doing positive work on the spring means the potential energy of the spring is increasing. Here we saw that the hand force is doing negative work on the spring, and intuitively we understand that the potential energy of the spring is decreasing, right? If the spring is less stretched, it's got less energy. It's not going to fly back as fast, right? Okay, and so all of this can kind of be boiled down to the following. We can say that the work done on a spring, the work done on a spring, if we stretch it further, that implies we're doing positive work. And if we compress it further, right, if we compress it further, that also implies positive work. Right, stretching further means you're beyond the resting state. You've stretched it beyond that, and you stretch it further, you're doing positive work. Compress further means you've already pushed it in a little bit, now you're compressing it further. And if you do that, if you compress it more and more, positive work will result. And then the alternative to these two is relaxing. If I relax the spring further, then I do negative work. Right, and that makes sense, right? If the spring is being relaxed, that means it's getting closer to its resting state, and the potential energy in the spring is diminished. Okay, so all of this can kind of be injected into a nice little equation here. We say that if the work done on a spring is, and we can see that this would be the case, the work is equal to 1/2 the spring constant. The force there is going to be basically kx, and then times, and then we square that, so kx final squared minus 1/2 kx initial squared. So this is the work done on a spring, by the hand. If this is the case, then we see just from the previous argument that the reverse such scenario would be the work being done by a spring. Then the work done by a spring, this is on a spring, and so this is by a spring, is, and I'm going to call this work elastic, right? The elastic work done by a spring. This is going to be equal to 1/2 kx initial squared minus 1/2 kx final squared. Right? I guess I'll use initial and final here. So that's initial and final. So it's just reversed. Right? So they're the reverse of one another. Right? If the work done by the hand on the spring is negative, then the work done by the spring on the block is positive, right? Or the spring on the hand is positive, right? So they're just the reverse. Okay. All right. So this is how we think of work, of the elastic work idea, right? When we're talking about springs. So given WL to be the work done by a spring, we can also express, right? We can also express the work done by the spring in terms of the given quantities at the beginning and at the end of the displacement. Okay, so the quantities at the beginning and end of the displacement, right? And these are, again, what? 1/2 kx squared. Okay. And so we can talk about these as the elastic potential inertia. So U is equal to 1/2 kx squared. That's That's the elastic potential energy of a spring. Okay. And so the work, the elastic work done by a spring is equal to 1/2 kx1 squared minus 1/2 kx2 squared, which we would say is equal to u1 minus u2, which is equal to negative change in potential energy. Okay, and this aligns perfectly with our formulation of gravitational potential energy, and it should, right? The relationship between gravitational potential energy and work is going to be identical to the relationship between elastic potential energy and work. I mean, they're different forces, different scenarios entirely, but the physical principles involved are the same. Okay. So now remember what the work energy theorem says. The total work done is equal to the change in the kinetic energy, so K2 minus K1. Okay, and that's going to be, I mean, so this is the work energy theorem, and this is regardless of the forces acting on the body. If whether it be elastic forces or gravitational forces, this is the work energy theorem, right? And so what we say is that if the elastic force is the only force, right? So if the elastic force is the only force, then the total work will be equal to the work done by the elastic force, which will be equal to u1 minus u2, right? And so then we can obviously equate these two, right? And we could say that K2 minus K1 equals u1 minus u2, right? And just like before, we can write this instead as K1 plus U1 equals K2 plus U2. Right, so we get that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. Okay. Now this is only true if the elastic force is the only force acting on the body. Of course, if you got some other outside force, then you have to think about this differently. Okay. Now, if we were to boil that down further into the actual kinetic and potential energy equations, we would say K1 plus U1 equals K2 plus U2. And instead of K1, the way we represent that's kinetic energy, it's again 1/2 mv1 squared. And our elastic potential energy, in particular spring force, is 1/2 kx1 squared. Okay, and this is equal to 1/2 mv2 squared plus 1/2 kx2 squared. Okay. All right, and so the total mechanical energy of the system is preserved, and therefore it's conservative. All right, and so this is the elastic potential energy equivalent of what we saw in the previous section for gravitational potential energy. Right, now something to notice here in these models that we're looking at is that we give no consideration to the mass of the spring. Now, if the spring's mass relative to the block is not significant, then you won't be able to do this. These equations won't work, right? But if the spring's mass is very small relative to the block, then it becomes somewhat negligible. Now, in our models, in these equations, or the coming examples, we'll assume that the spring's mass is very nearly massless, right? I.e. massless. Right, so we'll be assuming what we call an ideal spring, meaning a spring that, it's everywhere uniform in terms of tension and also massless. Now, just like what we saw with gravitational potential energy and gravitational conservation of energy, if other forces are present, we kind of treat them in the same way. Right, we say that the work done by the elastic force plus work done by the other forces involved should be equal to the change in the kinetic energy, right? And so just like before, we really kind of think of this as K1 plus U1 plus work other equals K2 plus U2. Okay, and so just like before, it works the same way, right? The only thing that's really changed is that we're not talking about gravity anymore, we're talking about springs. But the only thing that's really changed formally here in these equations is how we account for the elastic potential energy. Instead of mgx or mgy, as we saw with gravitational potential energy, now it's 1/2 kx squared, right? For the way we account for the potential energy. Okay, let's work an example. Let's do an example. See how all this works out together. So let me write out the example. So we've got a mass sitting on basically this ideal spring scenario. So a mass of 0.2 kilograms sits on a frictionless track. Sits on a frictionless track connected to an ideal spring. So connected to an ideal spring with the spring constant equal to 5 Newton meters. 5 newtons per meter. You stretch the spring. You stretch the spring 0.1 meters and then release it. You then release it, right? And assume, right, you stretch it out, it has 0 velocity, and then you release it. What is the velocity of the mass after it's moved a little bit? So what is the velocity of the mass at x equals 0.08 meters, right? So it's just moved a little bit. How fast is it going? Right, so let's draw the picture. So it's just the exact model that we've been looking at. All right, so I've got my x equals 0 here. It's good to know where you are at in relation to that. And the starting point is, I've stretched it out, we'll say to here or something. This is obviously not drawn to scale. And this is 0.2 kilogram mass. And this is x equals 0.1 meters. Okay, and it's all stretched out. Okay, the spring is all stretched out. Now what we want to know is what's the speed of this thing? How fast is it moving? It's obviously going to be moving in that direction. How fast is it going to be going at this point? That's what we're after. We want to know, like, how fast is it going? Right, so it's at rest here. We let go of it, it snaps back. Right? How fast is it going? It's going to be accelerating all the way up to this spot here, right? And then it's going to start to decelerate. How fast is it? It starts out at 0. How fast has it gotten to just with this little stretch here? From going from 0.1 meters to 0.08 meters. So 0.02 meters worth of displacement. Okay, so just like when we were talking about gravitational potential energy, you really want to solve these kind of energy problems, you want to think about positions of the block, right? So what we'll call point 1 this. We'll say this is point 1. And then point 2 is just going to be this thing. And we're just interested in what's the energy content. This is a conservative system, frictionless track, right? Obviously, we don't have to worry about air or any resistance, and there's no external forces, just the spring force acting. Conservative system, what's the energy here? What's the energy here? We should be able to force out the energy will be the same, won't it? Since it's conservative, but what's the kinetic energy here? What's the potential energy here? What's the kinetic energy, potential energy here? We can force out what the velocity is going to be. Okay, and just kind of assuming people are seeing this for the first time, I really want to emphasize what's happening in both cases, right? So at point 1, all right, that's the scenario where you've got the block stretched out at 0.1 meters, like this. X equals 0 is way over here. And x equals 0.08 meters is there. Right, and so if we think about the energy of the system, you've got the total mechanical energy, you've got the kinetic energy, and you've got the potential energy. Now, right here, there's no velocity, right? So it's right before we let go of it. It's all potential energy, isn't it? Kinetic energy is 0, and so all of the energy of the system is loaded up as potential energy. The second we let go of it, that's going to start to change, and that potential energy is going to shift over into this guy, right? So then at point 2, right, so drawing these things out really helps you to kind of visualize what's going on here. You've got x equals 0 is here, and now the block has moved over to this position. Okay, this is 0.08 meters, and it was over here. Okay, so it was here just a second ago. Now it's gone. All right, so at point 2, it's begun to move. Now it's got some velocity. Right, so the energy in the system is going to be the same as before. It hasn't changed. But now the potential energy is less. It still has some. The spring is still stretched and still pulling it. Right, it will have potential energy up until it gets to this point, right? And then it'll have no potential energy. It'll have completely transferred all of its potential energy to kinetic energy by this point. Right, but at this midway point here, it's got some potential energy still, right? So that's still positive. But now it has some kinetic energy also. Okay, so just imagine that these two sum up. These two here must sum up to this, right? Okay. All right. Okay, so that's kind of the setup, and it's a pretty simple setup, I suppose. I'm really languishing on it because I want to make sure everybody understands, can think about what's happening to the block at each point here, right? Because as soon as you can visualize that stuff, you can solve these problems like super easily. Okay, so let's think about point 1. What's going on at point 1? Right, so we know the picture. We know that the kinetic energy is equal to 0 at point 1. What's the potential energy equal to? So K1 is equal to 0. What's U1? Well, it's 1/2 kx1 squared, which is 1/2. We know the spring constant is 5 newtons per meter. And the distance that's this thing has been stretched, we see is 0.1 meters. Okay, so it's 0.1 meters, and then we square that. Right, so you multiply all of that together, and you get 0.025 joules. And so the potential energy is 0.025 joules at point 1. Now what about point 2? Well, at point 2, things have changed. We've got both kinetic and potential energy, right? So let's think about the kinetic energy. It is 1/2 mv2 squared. So it's 1/2 0.2 kilograms. Now V2, we don't know. That's kind of what we're after. Okay, so all of this can be just written as 0.1 V2 squared. Right, this is the thing we need to solve for. U2, 1/2 kx2 squared. Right, and so that's 1/2 times 5 newtons per meter times 0.8 meters, right? So now the displacement is slightly smaller because we're closer to the normal state, right? And so you crank all that out and you get 0.016 joules. Okay, so there's no outside forces acting. It's just the spring on the frictionless track, and that being the case, we can use K1 plus U1 equals K2 plus U2. All right, and so if K1 plus U1 equals K2 plus U2, then we really need to know what's going on with K2, don't we? So we can solve for K2. K2 will be equal to K1 plus U1 minus U2. And what are all those quantities? They are 0 joules plus 0.025 joules, and then minus U2, which we found to be 0.016 joules. Okay, and so all of those together are 0.009 joules. So the kinetic energy at point 2 is 0.009 joules. So K2 equals 0.009 joules implies that 1/2 mv2 squared equals 0.009 joules. And we saw before that K2 is equal to 0.1 v2 squared, and so that's 0.009 joules. And so we can kind of multiply all this together, and what we see is that v2 is equal to plus or minus the square root of, well, 2 times 0.009 joules over 0.2 kilograms. Apologies, I kind of reverted back to the original instead of using this. So it's all the same. I mean, this is just 1/2 of 0.2 kilograms. So, but you know, and so that all works out to be plus or minus 0.30 meters per second. This is a velocity, remember. Okay, and so the mass is moving leftward, right? It's trying to return to its normal state. And so what technically we would say is the velocity is negative 0.3 meters per second at position x equals 0.8 meters. 0.08 meters. Nope, sorry, Jiminy Christmas. Is it 0.8 meters? 0.08 meters, yeah. Sorry, I think I had a typo up above here. I think on the previous page I might have been using 0.8. It's 0.08, so apologies on that one. Okay, very good. Okay, so that's kind of a simple, I mean, again, that looks a lot like what you would have seen in the previous section. So if you followed all that, this is just a different way of writing the potential energy, but it's really the same kind of problem, isn't it? All right, so what we want to do, I want to do 2 more examples where we kind of elaborate on this example. So for this next example, I want to assume the same setup as the previous example, but this time, let's assume that there is an external force that's constant that pushes the block to the right. So, right, assume all the conditions of the previous example, but introduce a constant, and I'm going to say 0.61 newtons force to the right. Okay, so what is this? So what's going on now? All right, so I've got my block, and there's x equals 0 here, right? And so it's just sitting there, totally at rest, and a force comes along and starts pushing it. To the right, right? And it's connected to the spring, right? So when it starts to get out here a ways, you've got kind of 2 things acting on it. You've got the force, 0.61 newtons, and then you've got the spring force. And they're kind of fighting it out here, right? Okay, and so I'm gonna have this force be applied against the spring, stretching the spring to the right. And the question is, so here's x equals 0, and let's say over here I've got x equals 0.1 meters. What's the velocity of the block when it reaches this point now, right? So presumably 6.1 meters, 0.61 newtons is going to overcome the spring force if it starts to move this direction, right? You know, at some point the spring force will probably overtake this force, but given these 2 forces, what is the velocity? How fast is this thing going here? You know, maybe the spring force has already overtaken it and pulling it back this way, or maybe not. Maybe this F equals 0.61 newtons continues to push the block to the right. So in this scenario, it's important to keep in mind that the spring force and the external force are at odds with one another, right? They're opposite. Okay, so we're going to let point 1 be here. And then we'll let this be point 2, in point of interest 2. So we need the energy values here. We need the energy values here. Okay. So what's going on at point 1? Well, the kinetic energy is, we'll say it's 0. It's right before the force is applied, we'll say. And the potential energy there is also 0, right? Meaning there's no, the spring is in its resting state. So if you let go of the spring, nothing happens. So 0 joules for both of those. Now what about point 2? Just in terms of the spring kinetic and potential energy. We'll think about the external force separately. That's work other, right? But K2 is equal to 1/2 mv2 squared, which is 1/2 0.2 kilograms v2 squared. And again, this is what we're looking for. Okay, so we're going to be solving for that. What about U2? That's the potential energy of the spring there. 1/2 kx2 squared. So that's 1/2 times 5 newtons per meter times 0.1 meters squared. And again, we get 0.025 joules. We had that from the previous example. Okay. Now in this case, we can calculate the work done by the external force. All right, so we got to consider this external force. Work other is equal to this force times the displacement. And they're aligned, right? The force is perfectly pushing to the right, right? So we don't have to worry about the cosine of the angle between them, right? So this is just equal to 0.61 newtons times 0.1 meters. So the force is in newtons and the displacement is meters. And so this is 0.061 joules to the right, right? So we'll let it be positive. Okay, and so what is our equation? Well, K1 plus U1 plus work other equals K2 plus U2. Okay, and again, we need to solve for K2, right, because we're after this. So K2 is equal to K1 plus U1 plus work other minus U2. Right, and we have all of those quantities. So K2 is equal to 0 joules plus 0 joules plus work other, which is 0.061 joules, and minus the potential energy at point 2, which is in the opposite direction, right? And that is 0.025 joules. All right, so all of that together is 0.036 joules. Okay, and so again, it's kind of like the previous one. We need to figure out the velocity in this. So K2 we know is equal to 1/2 mv2 squared, which is equal to 1/2 times 0.2 kilograms times v2 squared, and we know all of that is equal to this 0.036. Okay, and so v2 is equal to plus or minus the square root of 2 times the work here, 0.036 joules, divided by 0.2 kilograms. Okay, and then when you do all of this, you see that you get plus or minus 0.6 meters per second. Right, so this indicates that the block will continue to move. So the spring force hasn't overtaken the spring force hasn't overtaken the force, the external force here, right? Because there's still some rightward velocity of 0.6 meters. Okay. Alrighty. And then one more example related to this, kind of a trickier scenario. Let's assume that the force that we just talked about is completely removed when the block hits that x equals 0.1 meter mark. The question is, how much further beyond that will it slide before stopping and reversing direction? Okay, so I've got the same scenario. X equals 0 is way over here. X equals 0.1 meters is here, right? And so the block is stretching the spring, right? So the spring is being stretched, it's pulling it back, but there's this force that's applied, right? This force is being applied here, and the force is going to, as we just saw, generate some velocity. It's going to be moving at approximately 0.06 meters per second at this point. Now, if I completely remove the force at that point and just let the block go, what's going to happen? Well, it's going to continue on for some distance. It's going to continue on for some distance in this direction. And the question is, how far? How far will it go, right? Because with this force removed, then the only force acting on the block is the spring force, and the spring force is in that direction, so you got a net force to the left, and so the acceleration throughout this region is going to be to the left. But the velocity we saw earlier, just be it will be in the rightward direction for some amount of time. So how long will it take before that acceleration pulls it back? Right, the spring force pulls it back. So if we remove the external force at x equals 0.1 meters, how far will the block slide before stopping and reversing directions? Is that clear? Hopefully that's clear. Okay. So point 1 is going to be here. Sorry, I gotta kind of write through here. Point 1 is going to be at the point where the external force is removed, and then point 2 is over here. So we actually don't know where point 2 is on the track. That's specifically what we're after. We know everything else about that point. We know all of the energy quantities. We know the velocities. We know, obviously, the masses and everything. So what we don't know is how far it slides. And that's what we're going to solve for. Right? So at point 1, okay, x equals 0.1 meters. We have the quantities from the previous section, right? We know that the kinetic energy at point 1 is 0.036 joules, right? We calculated this, and the potential energy at that point is 0.025 joules, right? And this is from the previous section. What about point 2? Well, okay, so something to consider, right? Something, I'm sorry I didn't say this first, but when the hand is removed, when the external force is removed, this becomes a conservative system, doesn't it? There's no external forces. It's just the spring force acting at this point, right? The block will continue to move. The only force acting on it will be the spring force, which pulls it back. It'll continue to move for some distance and come back. This force has been completely removed from the scenario as soon as we hit this displacement, right? So that's important. I apologize for not stating that. That's a key thing to note here. Okay. So really, it's going to be a K1 plus U1 equals K2 plus U2 kind of problem, right? There's no work other at this in this part of the problem. Right, so point 2 is x equals, I don't quite know, the point on the track where the block stops and turns around. So let's think about the quantities there. K2 would be 1/2 mv2 squared, which is equal to 1/2. The mass is 0.2 kilograms. Now what's the velocity at this hypothetical 0.2? Well, presumably it just stopped, didn't it? It's slowed down throughout this range, and then it stopped, and now it's going to go back. All right, so the velocity here is 0. So this is 0 meters per second, right? So this is 0 joules. So the kinetic energy at 0.2 should be 0, which means all of the energy should be in U2. Okay, so U2 is going to be equal to 1/2 kx2 squared. Okay, and so that is 1/2 5 newtons per meter x2 squared. Okay. And this is equal to 2.5 times x2 squared. Okay, so then we just kind of set this up, right? So it's k1 plus u1 equals k2 plus u2. We really need to solve in this case for u2, right? But let's just plug in the energy quantities. Let's just do it this way. 0.036 joules plus 0.025 joules is equal to the kinetic energy at 0.2, which is 0 joules. And then U2 we see is this 2.5 x2 squared, right? And so we can just solve for that directly here. So this being the case, then x2 is equal to plus or minus the square root of these two. So 0.036 joules plus 0.025 joules divided by this 2.5. Okay, and so these are joules divided by, now that's technically a newtons per meter. And so when you divide all that down, you do get meters. And so you see this is 0.156 meters. Right? And so the mass is going to continue to move past this 0.1 meters. It's going to continue to move an additional 0.156 meters. So this distance here is going to be 0.156 meters. Oh, actually, I think that's the distance from here all the way over. Yes, careful of that. Right, so this whole distance here is 0.156 meters. Right, because that's the total displacement of the spring, the end of the spring. Right, so it looks like technically this thing's going to move about 0.056 meters beyond this point. Okay, so there you go. 3 very, very good examples of the elastic potential energy. And I think we'll end this lecture there. In the next section, we'll continue to we'll kind of elaborate a little bit more on conservative and non-conservative forces. It'll be a little more conversational than this one, but very useful, important for kind of tying up some loose ends on these concepts. So until then, take care.